Hi everyone. The topic for this unit is quadrilaterals, and the shape that we're going to be discussing today is the parallelogram. So the parallelogram is in um, this branch of the quadrilateral family tree, as we call it. And what's interesting about this hierarchy is that what happens is each figure another on the family tree, retains all of the properties of the figure above it. So what I mean by that is a parallelogram is a quadrilateral, right? And a rectangle is a parallelogram, meaning a rectangle has all the properties of a parallelogram. A rhombus is also a parallelogram, but a rhombus is not a rectangle. You see, they have no connection on the hierarchy. And then we can say a square is a rhombus or a rectangle. We can also say a square is a parallelogram, but we can't kind of go the other way. We can't say a rectangle is a square because a rectangle does not retain all of the properties of a square. So it's not too important at this point to totally understand this. I think it will make more sense as we discuss many of the other figures and their properties. But for this lesson, we're going to focus on the parallelogram, this figure right here. So a parallelogram is a quadrilateral with two pairs of parallel sides. Some of the properties are that the opposite sides are congruent. So I'll draw that in. The opposite sides are congruent. So we could say AD and BC are congruent. And also AB and DC are congruent. Opposite angles are also congruent. So therefore we can say that angle A is congruent to angle C, and angle D is congruent to angle B. Also, consecutive angles are supplementary, meaning angle A and angle B equal 180. Angle D and angle C equal 180. Angle A and angle D equal 180. And finally, angle B and angle C add to 180. So I'll just draw a little arrow there. Finally, we see that diagonals bisect each other. So if we have this point in the middle E, we see a diagonal AC and a diagonal DB. These intersect at point E, and they bisect each other, so we can say that DE and EB are congruent, and AE and EC are congruent. So what we usually do is apply these properties to solve problems or do proofs. So in our first couple of examples, we are given a parallelogram because we are told ABCD is a parallelogram, and we're asked to find the measure of each angle. So clearly we have to solve for y, and we look at this figure and we notice that this angle B and this angle A are consecutive angles. So we can create an equation. So the equation would be these consecutive angles are supplementary, so we can say that 6y plus 5 plus 10y minus 1 equals to 180 degrees. So now we solve this equation for y. We can combine our terms with y. So I could say 6y plus 10y is 16y. And our constants, 5 and 1. So 5 minus 1 is 4. And now we just continue to solve. So we use inverse operations, subtract 4 from each side to get 16y is equal to 176. Divide by 16, and we see that y is 11. So if we want to find the measure of ABC, we're simply going to plug in. We see angle ABC is 6y plus 5. So I'm going to say 6 times, we know y is 11, so plug in 11, plus 5. 6 times 11 is 66. 66 plus 5 is 71. So angle ABC is 71 degrees. We are also asked for the measure of angle BCD. So angle BCD is actually this one over here. So we're actually not given an equation, but we know, based on the properties of a parallelogram, that angle B and angle C are supplementary. So we can simply say 180 minus 71 gives me the angle measure of C, which is 109 degrees. So that's how you would use it to solve for an angle measure given consecutive angles. Let's take a look at another problem. So in this problem, we're given a couple different angle measures within the parallelogram, and we're asked to find other angle measures that are not given. So we know, based on this diagram, we know a few things. We know that this side here, MN, is parallel to LP. We also know that ML is parallel to NP. So we can kind of use this information and some of our previous knowledge to determine the measure of other angles within the diagram. So there's a couple different ways you can do this. You could use the interior angle of the triangle theorem, meaning because we can see we have 4 different triangles in this diagram that are created by our diagonals. So we can use that theorem to find the measure of missing angles, or we could use our knowledge of parallel lines and transversals. So I'm going to do this using parallel lines and transversals and the triangle interior angle theorem. So I'm going to start by determining LPM. So LPM is this length, this one over here, this angle over here, LPM. And I know that these two lines, right, I know that MN and LP are parallel. And if I kind of traced this transversal a little longer, maybe, so you can see that, I can see that it kind of creates this, this set of parallel lines being cut by a transversal. And now we see, right here, we see alternate interior angles. We know from earlier in this year that alternate interior angles are congruent, so I can say that the measure of this angle here, QMN, is the same as the measure of angle LPM. So I'm just going to say this measure is also 62 degrees based on the alternate interior angle theorem. So let's look at another one. We have angle MLP. So MLP is over here. MLP. So there's a couple different things we could do. We could once again use the alternate interior angle theorem. So we see here again we have this transversal by cutting these two parallel lines, MN and LP. So we know that this is 40 degrees, and therefore we know that this is also 40 degrees because alternate interior angles are congruent. So we know this piece is 40, we know this, and we're missing one more piece to tell us the measure of MLP. So there's a couple different ways you can think about this. I'm going to use the alternate interior angles theorem again, because again, we see two sets of parallel lines. We see another set of parallel lines, LM and PN, right here. If we kind of turn this diagram to the side. So we see this measure of this angle here is 32. This is angle PNQ. So I know that this angle here, this other piece, QLM, is also 32 degrees, again, by the alternate interior angles theorem. So therefore, the measure of MLP, this whole thing, MLP, which is this entire piece, maybe I should have highlighted this in the beginning, this one. MLP is going to be the sum of 32 and 40. So I'm just going to say 32 plus 40 is 72 degrees. Next, we need to find MQN. MQN, that's this one located right here. I'll highlight it. So our diagram's getting a little bit messy. Maybe I'll actually erase a little bit of this first so we can see a little bit better. Yeah, I think that will help a little bit. Okay. So now we're looking for this one, MQN. And we already know two of the angles within this triangle MQN, this whole thing. So we know that the interior angles of a triangle sum to 180 degrees. We know this is 62. We know this one is 40. So we can simply say 180 minus the sum of 62 and 40. And we know 62 plus 40 is 102. So 180 minus 102 gives me 78 degrees. So this measure is 78 degrees. Lastly, we need MQL. So MQL, let's highlight this one, different color. MQL is this one right here. Well, there's a couple ways we can go about this. Let's just say, well, we see that we know MQN is 78. We know that this angle here, LQM, and angle MQN, they form a line. And we know that a line is 180 degrees. So I can just say 180 minus 78, right? Which is 102 degrees. So here are all our angle measures in this diagram. And are there other ways to do this? Yes, absolutely. You could go about this using the triangle interior angles theorem the whole way around and find every angle and do it that way if you don't remember the alternate interior angles theorem. And that would also be perfectly fine. Let's look at one last example. So now we're asked to find some side lanes. So MNPL is a parallelogram. NM is 10, ML is 12, MQ is 6, and LQ is 9. Find each angle measure. Sorry, not angle. Find each measure. So we're actually finding segment measures here. NP, QN, and MP. So we know a couple things. We know one of the properties of a parallelogram is that the opposite sides are congruent. So therefore, I know that ML is congruent to NP. I also know that LP is congruent to MN. So that might help us. So the first one says, what's the measure of NP? Well, I know ML is 10. So therefore, I know ML is 12. So therefore, I know NP is also 12. The next question asks for the length of QN. So QN we can see is a part of the diagonal LN, and we see this other diagonal is intersecting in the middle at Q. Well, one of the properties of a parallelogram is that the diagonals bisect each other. So I know that MQ and QP are the same. And then I also know, I have to use 4 here, because that LQ and QN are the same. So I know QP is 6, and I know QN is 9. So QN is 9. And lastly, we're asked for the length of MP. Well, MP is this whole entire piece, right? So this whole thing. Well, I know that MQ is 6. I know that QP is 6. So the sum of 6 and 6 is 12. So MP is 12. Okay, let me know if you have any questions about this. I know the video is quite long. I'll put the timestamps in at the bottom so you can skip around as needed. And let me know in the comments if you have any questions or in class. Thank you.